All right, let's talk about velocity time graphs. Now, that might sound a little technical, but trust me, they're an incredibly powerful tool for understanding the whole story of how something moves. And by the end of this, you'll be able to look at one simple line on a chart and see everything from a gentle cruise to a sudden screeching halt. So, picture this. You're watching a race, and these two motorcycles just blast past you. I mean, they are obviously moving fast. But just saying they're fast doesn't really tell you the whole story, does it? Especially when they're actively speeding up like this. So that's the real question, right? The one that scientists and engineers really care about. It's not just about how fast they are, but how do we actually measure how fast they're getting faster? That's the idea we're going to dig into. Okay, so before we can really jump into reading the graph, we got to lay down some groundwork. We need to get on the same page about three key ideas: speed, velocity, and the big one for today, acceleration. First up is speed. This one's easy. We all get this. It's just how fast you're going. You know, you look at the speedometer in your car, it says 30 meters per second. Simple as that. It's just a number. Now, next we have velocity. And it's almost the exact same thing as speed, but with one tiny but super important addition: direction. So you're not just going 30 meters per second, you're going 30 meters per second north. That little detail is going to be really important in a second. And that brings us to the star of the show, acceleration. Acceleration isn't about how fast you're going right now, it's all about how quickly your velocity is changing. You know, when you put your foot on the gas, you're accelerating. When you slam on the brakes, you're also accelerating, just, in a negative direction. It's all about that change. So we know what acceleration is, but how do we actually put a number on it? Well, the classic way, the math class way, is to use a really simple formula that just breaks it all down for us. And here it is. Don't let the letters scare you. It's actually super simple. It just says that A, which is acceleration, equals the change in velocity, that's your final velocity v, minus your starting velocity u, and then you just divide all of that by t, the time it took to make that change. Let's just run through a quick example. Imagine a car starts from a dead stop, so its initial velocity is 0. It then hits 10 meters per second, and it does that in 2 seconds. So you just plug in the numbers. The change in velocity is 10 minus 0, and we divide that whole thing by the 2 seconds it took. And the answer you get is 5. But 5 what? The units here are meters per second squared. Now what on earth does that mean? Well, it's simpler than it sounds. It just means that for every single second that goes by, the car's velocity goes up by another 5 meters per second. That's acceleration. So a formula is great. It gives you a nice, clean number. But what if you want to see the whole journey? What if you want to feel the motion? Well, that's where a picture, a graph, becomes so useful. Yeah, that formula gave us a single number for acceleration. But what if we could show that whole 2-second trip and everything that happens before or after, all in one simple picture? And this is it. This is the velocity time graph. You've got time running along the bottom and velocity going up the side. And that red line, that's our car's journey. See, it starts at 0 seconds with 0 velocity, and then 2 seconds later, boom, it's hit 10 meters per second. Okay, get ready, because here comes the really cool part. This is where it all clicks. This graph isn't just a drawing, it's secretly a calculator. And the answer we're looking for, acceleration, is hiding in plain sight in the steepness of that line. This right here is the absolute key to everything. The steepness of that line, what mathematicians call the gradient or the slope, that is the acceleration. That's it. A really steep line means a really high acceleration. A less steep line means a lower one. And figuring out that gradient is super easy. You probably heard this in school. It's just rise over run. The rise is how much the line goes up, which is our change in velocity. And the run is how much it goes across, which is just the time that's passed. So let's put our two methods side by side. Over on the left, we've got our formula, which gave us 5. Now, on the right, let's use the graph. The rise, our change in velocity, is 10. The run, our change in time, is 2. And what's 10 divided by 2? It's 5. It's the exact same answer. See? The graph isn't a different method. It's just a picture of the same exact math. Okay, so we've totally mastered reading a simple straight line. But let's be honest, most real journeys have starts and stops and bits where you're just cruising along. So let's look at a graph that tells a much more interesting story. This graph right here tells a whole story. It's got a beginning, a middle, and an end. Just by looking at the shape of this line, you can see the object speeds up, then it travels at a nice steady pace, and then it slows back down again. Let's break it down. In the first part, the line slopes up. That means velocity is increasing, so we have positive acceleration. It's speeding up. Then in part 2, whoa, the line is totally flat. It's not rising at all, so its slope is 0. That means the velocity isn't changing, it's moving at a constant speed, so 0 acceleration. And finally, in part 3, the line slopes down. Velocity is decreasing, which means our object is slowing down. We call that negative acceleration. So if you only remember one thing from all of this, let it be this. The slope of the line on a velocity time graph is the acceleration. Period. A slope that goes up means you're speeding up, a flat slope means you're cruising, and a slope that goes down means you're slowing down. It's the magic key to reading the whole journey. Now, everything we've looked at so far has involved nice straight lines. And a straight line means that the acceleration itself is constant. But that gets you thinking, doesn't it? What if the acceleration isn't constant? What if it's changing too? What would that look like? Well, it would look like a curve. This graph of a motorboat slowing down shows us that its acceleration is changing from moment to moment. Now, how you read the story that a curve tells, well, that's a fantastic story for another day. Thanks for joining me.